We're going to develop the formula for electric potential energy. So consider a charge here. Let's call that Q1, and a distance r from there. We have another charge Q2. So Q1 and Q2 are measures of how much electric charge we have. That would be measured in coulombs. That's the SI unit for charge. And we want to consider how much work it would take to bring a charge from infinitely far away. So let's say it was here, to bring it from infinitely far away to there. And remember, work is force multiplied by distance, but we have a changing force, so we have to use integration instead of just simple multiplication. We define the amount of energy when we're infinitely far away as 0. So that means the energy at r, the electric energy when we are a distance r, so I'm writing this as a function, that doesn't mean multiply. And that's going to be defined as the negative of the amount of work to bring the charge, to bring it from infinity, to bring, sorry, I'm missing the R, to bring from infinitely far away. Okay, so how am I going to find the work? The work is what we get when we add up every step from being infinitely far away to our distance r of the force multiplied by the step that we take. So the way this works is the dx values are the little steps we're taking. We start infinitely far away and we take a bunch of steps, and we're saying the distance of each of those steps is dx. I'm going to take a whole bunch of dx's and I'm going to multiply it by the force when we're at that distance away. And the reason why we can't just do this all in one fell swoop is, one, we're multiplying by infinity, and two, we've got this changing force. So this symbol here means multiply the force at each point by the tiny little step, and then add them all together as we go from a distance infinitely far away to our distance r away from that charge. Now the force is, this is an electrostatic force, so we're going to add up from being infinitely far away to distance r. We're going to add up the electrostatic constant times Q1 times Q2 all over x squared, because when we're distance x away, that's the force that we're looking at. And we're going to multiply that by dx. So perhaps you remember, as we developed this from gravity, the way we deal with these is we take a good look at this function and we try and imagine what is that the derivative of. So think of a function of x that has k q1 q2 over x squared as its derivative. And if you write that out where divided by x squared is the same as x to the negative 2, it makes it a lot easier to guess what that would look like. And so it turns out that what we're looking for is negative k q1 q2 over x. And we're going to evaluate that from infinity all the way to r. If you're a little bit unsure at this point, and you're an introductory physics student, perhaps you've not seen integration yet, that's okay. I just want you to get a sense of what's happening for the development of the formula, as opposed to just taking the formula and using it. I want you to get a sense of it. That doesn't necessarily mean you're going to be able to develop all of this yourself. You will soon once you study the other half of calculus. However, to see that you understand in principle what's going on here, perhaps you can verify that if you take this and you take its derivative, so you take the derivative d dx it, find the derivative of this, it should give you that. Verify that for yourself, and that's probably a good enough full understanding at this point. And then come back and look at this later after you've learned integral calculus, and you should make a lot more sense of it. So we're now going to take this and we're going to evaluate it at r, and then subtract from that, evaluating it at infinity. So that's going to give us negative k q1 q2 over r minus negative k q1 q2. Now, this is a little bit sloppy math. You shouldn't just divide by infinity. You should write it as a limit, the limit as it approaches infinity. But just imagine this, you're dividing by an infinitely large number and the whole thing turns into 0. So that all scratches out. This means that the amount of work that it takes to get charge Q2 to a certain distance r from Q1, to get it there from infinity is actually a negative amount of work. And that is k q1 q2 over r. So the energy that we have, the potential energy, is going to be the negative of the work. That's how we defined it here. And so that's going to be k q1 q2 over r. And that's the electrostatic energy from two charges Q1, Q2 that are a distance r apart.